Okay, so question 6 of the Edexcel sample assessment material, paper 1 for GCSE physics. Figure 7 shows the nuclei of 4 atoms. Which 2 nuclei have the same number of neutrons? So we've got 3 different elements but 4 different atoms because these 2 are isotopes, so they're both uranium but with different number of neutrons. And the number of neutrons equals the mass number minus the atomic number. Because the mass number is the number of protons and neutrons, the atomic number is the number of protons, the difference between the two will give me the number of neutrons. So for this, we've got 234 minus 92. So the number of neutrons here, 234 minus 92, is 142. 235 minus 92 gives me 143 neutrons. 238 minus 94 gives me 144 neutrons, and 238 minus 95, hopefully it's one of those 3 numbers, is 143 neutrons. So uranium 235 and americium 238 is the answer you're looking for, which is answer B. State what is meant by the term half-life. This is just a definition you need to learn. It is the time taken for half a radioactive sample to decay. Plutonium-238 is used in spacecraft to provide heat to power generators. One of these generators contains 925 grams of plutonium-238 when it's manufactured. 1 gram of plutonium-238 has a power density of 0.54 W/G, that is watts per gram, which is going to be important for us. Plutonium-238 has a half-life of 87.7 years. Calculate the average energy release per second by the generator after 263 years. This hasn't got an equation. This is a problem-solving exercise that you're trying to work out with the units that you're given. So the average energy release per second, energy per second or energy over time is equal to power. So you want to work out what is the power after 263 years. Now to do that, we need to work out how much plutonium is left. So we have 925 grams of polonium when it's manufactured, and 263 years later that will have decayed. Now 263 years divided by 87.7, which is 1 half-life, comes out as 2.998, lots of numbers that basically rounds to 3. So they're asking us how much energy is left after 3 half-lives. So every half-life, half the sample decay. So after 1 half-life, 925 is halved. So divide by 2, and we have that it is 462.5 grams after 1 half-life. After the second half-life, divide that by 2 again, and we get 231.25 grams. And after the third half-life, divide by 2 again, we get 115.625 grams. So this is how much mass is left of plutonium. Now each gram gives me 0.54 watts, so the power of 115.625 grams is 115.625 times or multiplied by that density 0.54, which comes out as 62.4 watts. They want to know the energy per second, but the energy per second is the power. That's what the definition of power is. So our answer is 62.4. 62.4 watts means that every second 62.4 joules of energy is released. Part C, the nucleus of americium 238 can absorb an electron. When this happens, one of the protons in the nucleus becomes a neutron, as shown in figure 8. So this is an example of beta plus decay in a slightly different way than usual of explaining it. So describe how absorbing an electron affects the proton number and the nucleon number of a nucleus. So when an electron is absorbed, a proton turns into a neutron. So the proton number decreases by 1. Because one of the protons you did have has now become a neutron, so there's 1 less proton. The number of neutrons increases by 1, but there isn't a neutron number, there's just a mass number, and that's the number of protons and neutrons. If I've decreased my protons by 1, but I've increased my neutrons by 1, the mass number stays the same. So this is the opposite to what happens in beta minus decay when a neutron turns into a proton and electron. And there the proton number increases by 1 and the mass number stays the same. Deduce which nucleus is formed when americium-238 absorbs an electron. So let's go back to this page. We know that americium, I'm going to do it down here, is 23895. And we're going to absorb an electron. So I'm going to add 0 minus 1e. And I'm going to make a sum. So 95 minus 1 is 94. 238 plus 0 is 238. So if I go back to this page here, is there anything that's got 238 and 94? Oh, there is. It's Pu, plutonium. And the answer is there, plutonium 238. There we are. It's quite a tricky question.